kinetically constrained spin on how low scaling it can be at criticality, please.
Thank you. So just to mention, I'm French. I'm not Italian. Okay, and my name is Cyrille and not Roberto. Roberto is my family name. Okay, but I'm very happy to work with Italian people. So, so let me start with the model. So we will consider the tree. So let me draw the binary tree, but it could be a regular carry tree. So all along the tall k will be just 2, but all the results will hold for general k. So so this is a tree, and I will consider spin system. So I have configuration. The state space is just 0, 1 to the t, and given a configuration in omega and x in t, sigma of x is either 0 or 1. So if it's 1, I will say that the site x is filled, or there is a particle at x. And if the configuration at x is 0, I will say that x is empty. Okay, so so we have 0 and 1s. And so we would like to run a dynamics on this. And so the dynamics is as follows. Each site waits mean 1 exponential time independently. And when the ring clock the clock rings at some point, so say here, the site look at the children, the 2 children, and you ask for both children to be empty to make an update. Okay, so in that case, this guy will do nothing. This guy will do the update. Okay, and what is the update? You just forget about the configuration at the site, so you forget about the 0, and with probability p, you put a 1. With probability 1 minus p, which I would call q, you put a 0. Okay, and again, if one of the 2 children is 1 or 2 children are 1, you don't do anything. So the generator of this dynamics is the following. So you just the sum of all sites in the tree, and so then you put the equilibrium with respect to a Bernoulli measure. So this depends on sigma. So let me write this again. Okay, so mu x is just a Bernoulli p measure. So p is some parameter. It's infinite. For the moment, it will be finite later on, but for now, it's infinite. Okay. So, and what is Cx of sigma? So Cx is the constraint. It's either 1 or 0. So it's 1 if all the children of x are empty, and 0 otherwise. Okay, is it clear for everybody the dynamics? So again, each site waits a mean 1 exponential time. When the clock rings, you look at the children, and both must be empty to do an update. Okay, so probably you already guessed, the more 1 you have in the system, and the slower the system is, right? And in particular, if you look at your tree, if you start with all 1s, the dynamic will never move at all. Okay, and also if you want to change something at this point, you will first wait to put some 0 here, and so you have to go down and look for the first line of 0 you can fine and go up. Yes?
Why do you say when it's all once it doesn't move? Doesn't the bottom guy move?
Well, the tree is infinite, so
Okay, fine. Okay.
well, at some point it will be finite, and we will put some boundary condition which will be empty, but so it's infinite. Okay. So so the dynamic L is symmetric in L2 of mu, where mu is just the product measure of Bernoulli measure. Okay, so here contrary to the Ising model or this kind of model, statistical model, where the measure itself is hard to handle with. Here the measure is just the product measure. So the problem are coming from the dynamic itself, not from the measure. Okay, there is no static actually. Okay, so the problem is understand the long time behavior. Okay, so maybe again, if Q is small, the dynamic is slowed down. Okay, so a bit of history about this model. So as it is, this has been introduced by Aldous and Diaconis, 2002, where they were actually dealing with another model called the East model, which is a one-dimensional model. They computed the spectral gap of such a model, and I will say that in a minute. This is part of a more general class of model called kinetically constrained model. So there is this one-dimensional model, which is the East model, but there is also a two-dimensional model, which is the North-East model. So you do the same. Each side of the grid waits some exponential time, and when you want to do an update, you look at the East and the North neighbor, and you ask for both of them to be empty. So they introduced this model as a kind of toy model for this northeast, okay? Because you are on the tree, so things should be easier. Okay, so as I said, so the model is part of a larger family of kinetically constrained models. So this model has been introduced by physicists in the 80s in order to model the liquid glass transition. So the idea behind this transition is that the glass transition might be only a dynamical transition. So if you take your liquid and you slow down the temperature very quickly, the move of the particle cannot occur easily, and so you cannot reach a crystal or some homogeneous structure. So your liquid is just stuck in some heterogeneous situation, which is called amorphous solid, and this is supposed to be the glass. So these systems here, this family, were exactly devised to mimic this phenomena. So this is the point. In order to make a move, you need space, so you need empty sites, and you have some block structures. Okay, like as I said, all ones is blocked forever. So let me say maybe a few names here, if you want to go from the literature. So if you are interested in So there are many others. If you're interested, these two guys, they did some survey in 2003 about this kind of these models. Okay. So let me introduce some map, the bootstrap map that I will use later on. So there is a classical result that says that the two assertions are equivalent. So 0 is a simple eigenvalue of L and TF of sigma. So sigma t is the evolution of the process time t. This converges to mu of f, where mu is the product of Bernoulli measure in L2 for all f in L2. So there is convergence. Okay. So so let me introduce some PC, which will be just the supremum over all p, such that 0 is a simple eigenvalue of L. And we would like to understand what is exactly this quantity. So for that, I will introduce the bootstrap map.
Can I ask a quick question?
Yes?
Maybe you said this, but so you have two stationary distributions, mu and the point mass at all ones.
Actually, there are many of them.
That's what's going to, besides complex combinations, you still have many others.
Yeah. Any infinite cluster will be stacked, so you can, you can invent a lot of block configurations. So the point is, if you start from mu, then depending on the parameter p, you will have clusters or not. So actually, the bootstrap map will just give you this. But probably you already guessed, if you are below 1/2, things will be fine for you, because the clusters will be just finite. If you are above 1/2, you will find an infinite cluster, and so you're not ergodic at all. So let me say that properly. So the bootstrap map is a deterministic map. So from a configuration in my state space, I have a new configuration, which is as follows. So this is 0. So the bootstrap map just wants you to have zeros. Okay, so you look at your configuration. If you have a 0, you just keep the 0. So it's 0 if sigma of x is 0. But also, if the original, your dynamics wanted to put a 0, or you're allowed to put a 0, so if the constraint is satisfied, like here, well, here now, okay, like here, this guy, so you also put a 0, okay? And you don't do anything for the rest. So if the constraint is satisfied, or you already is a 0, you put a 0. So if or x of sigma is 1. Okay, so you can look at the law starting from mu after n iteration of this map. So I will call this mu n. And it's possible to prove that actually this mu n converges to some mu infinity. I think probably the first to show that was shown. And so now I can define another quantity. So bootstrap percolation threshold, which would be the supremum over all p, such that with probability 1, say the root, so sigma of the root is 0. So if you look at you start with a configuration given by mu, okay? Then you apply the bootstrap map infinitely many times, and you ask that the root is empty at the end of this procedure. Okay, this with probability 1. Okay, so actually you can prove. So this is a result by Martinelli, and I should say that so there is two Toninelli, like Chris, two brother and sister in that case. So this is Cristina Toninelli, and not Fabio Toninelli. So it's the girl. So using some technique of the four of us on different models, so they adapt the technique to the tree. You can prove that both critical quantity actually equals, and they both equal 1/2, because of this quantity here is just the when do you know that the root is not empty at the end of the bootstrap? It must be part of an infinite cluster. Okay, so this quantity is known to be 1/2, and what you can prove is the two quantity equals. So more generally, it's 1/k if you are looking at KR3. So below 1/2, you have this convergence here, and above you don't. Okay. So we'd like to understand maybe a bit better what's going on in the long time behavior. So I will talk about spectral gap. Spectral gap. So let me introduce this. So if I call the Dirichlet form of a function which is mu of f minus mu of, which is just the sum over all x in t. So this is the Dirichlet form. The gap of my operator L is just the infimum over all f which are not constant. Maybe I should say here 0 is the again value associated to constant functions. If you take constant function here, you get 0. Okay. So you want to. So it's the Dirichlet form and the variance. So why is it interesting to look at this quantity? Because so a way to restate that is just to say that for any f you have this quantity, and actually this is exactly equivalent to the fact that the variance of PTF is less than exponential 2t, the spectral gap, the variance mu of f. So in particular, there is no hope to get such a result above 1/2. There is no spectral gap, and probably I should write it again. All depend on sigma. So since you don't have any spectral gap, you can try to look at the system on finite size. So now are coming finite tree. So take a tree of depth L. Then you want the system to be ergodic. So here you have the boundary. You just put all 0 here. So in other words, the constraint here at that site are always satisfied. Okay, so I will change the generator L in L sub L, which is exactly the same, but now I have a new constraint which is the same as before, except that on the boundary the constraint is always satisfied. Okay, so this guy here equals that one, except on the boundary where it's always 1. So you can define again the gap inside this system. So let me call it gap. So the gap of L minus 1. Okay. So now comes the conjecture by Aldous and Diaconis about the spectral gap. So here, in that case, the invariant measured is just the product measure on the finite tree. So conjecture. So the conjecture is the following. If P is less than 1/2, then the gap of L is just a constant uniformly in L. In other words, the gap over there is just constant. So if P equals 1/2, so at criticality, the gap, so here is the conjecture, the gap should be 1 over L squared. So order of 1 over L squared. So polynomial. And if P is larger than 1/2, then the gap should be exponential. Sorry. Or something. Okay, so here is the picture. So 1 and 3 actually are part of the paper here. So 1 and 3 are proved in 1 and 3 addressed in so what I would like to talk about is this result at criticality.
Order means exactly above.
Sorry?
Order of 1 over L squared means exactly.
Well, I mean bounded above and below by some constant times this. Well, we don't have this result. It's too much. What we have is this. So here is the theorem. So fix P equals 1/2. Then there exists some power beta, so positive, such that for any k, so remember we took k equal 2, but it's all for any k. There exists some c, so that depends on k and beta, such that the gap is in between 1 over L 2 plus beta, so constant over L over 2. Here is the result we get. So this is the first result. The second is a quasi-critical case.
Sorry, what was the candidate before larger? So K bigger than
KL?
Sorry?
What's K?
Oh, so K. So at the beginning, I said we can deal with a K-ary tree instead of the B-ary tree.
But then what is P for general K? Is it still a half?
It's 1 over K.
Ah, sorry.
So yes, okay. So let's forget about K. So there exists beta and C such that.
No, but you could just as well have written P equals 1 over
Yes. No, but I don't want to confuse anyone. Yeah, no, you're right. Okay, you have the result with any K. And maybe this is important because the constant beta does not depend on K. I wanted to emphasize that. And so now fix P less than PC, so 1 over 2. So then again, so I don't remember, maybe it's beta plus 1. So then there exists some constant, 2 constant, such that the gap of the infinite system now behaves like constant times P minus PC over 2 and P minus PC over 2 plus alpha. Two or three? Yes. So what? Yes, PC minus P. So when you approaches the critical point, you do it in a polynomial way. Okay, I will not prove that. I will try to give some idea of the proof of this. But just before that, so remember what is the bootstrap map because I will use it. Let me mention 2 papers that are related to that. So related papers. So one is by Lubetsky, and Yuval Perez. So I don't know. 11 probably. So here they are dealing with the Ising model on 3, so the same as us at criticality. And they prove more or less the same type of result. So there exists a constant beta that does not depend on K, such that this is true. So again, here the difficulty is coming from the measure, so the static of the measure, not the dynamics. While here, for us, the measure is easy, but the dynamic is difficult. And there is also a paper by Lubetsky and Sly, 2012. So they are dealing with the Ising model at criticality on Z2. So again, they are proving some polynomial decay of the spectral gap in finite boxes. Okay, so let me go for some words of the proof. So I will just prove 1, maybe say something about 2, but very shortly. So proof of 1. So the proof goes uses a multi-scale analysis plus some auxiliary long-range dynamics. So some comparison argument. Probably I will just, okay. Okay, so yes. Yes, just before. So the upper bound, as usual, you just try to find a test function. So the upper bound, we use a test function. So what you use is you take the f of sigma, which is just the number of sites that are attached to the occupied cluster of ones to the root. Okay, so the number of sites of the cluster attached to the root. So here is the root. So you have some ones, maybe more than one. Maybe this one is 0, and so on. And so since you are dealing with the tree, actually you can compute more or less everything. So this function, you can prove that this is greater than constant times L to the cube. And so here is 1 over the gap that you are looking for, directly form. And what is the directly form? So 1 over the gap is just the sum of all x in the tree of length of depth L, mu of Cx. But now, how can this be different from 0? You just need to make a move just on the leaves of the cluster. If you're not on the leaf of one leaf, you cannot do any move. So this will be 0. So this is just less than some constant x is a leaf of the cluster, which is bounded by just the measure of the cluster itself, mu of f, and this you can compute is just proportional to L. So you get the upper bound. So for the lower bound, you use this multi-scale analysis. So let me go for that. Okay, so let me call little l just something that will be a little bit smaller than capital L. And so it will be some depth. And I introduce a new constraint, Cxl, sigma, which is 1 if I can do the following. So x is here. What I ask, I look below x. So depth, I will just need to go till depth L. And I ask if I use the bootstrap map L minus time, L times, or maybe L minus 1 times, I can empty the two guys here. Okay, so it's 1 if the true constraint of the bootstrap map applied L minus 1 times of sigma is 1. So in other words, if using L times the bootstrap, I can put 2 0 here. Okay? So somehow this just show you that somewhere in the original configuration, you have some line of 0 here that you can use. And with less than L steps, you can put 2 0 here. L steps of the bootstrap map, okay? So you speed up very quickly the dynamics by that. The usual dynamics is you ask for 2 0. Here you ask for something much stronger, to have a line somewhere. Okay, so, and also the probability and the mu that this does not happen. So you can compute that explicitly, and it's of order 2 over L. So I will use it. So it's small, but it will be very useful. Okay, so so is the first lemma. Actually, the only one I will prove. So probably, if you're tired, it's a good point to start to sleep, because now I enter some technical. I'm afraid it will be a bit hard to follow. So please interrupt me or just sleep, whatever you like. So lemma is the variance will be less than some constant which depend on delta. So delta at the end will be small. Well, delta is just some parameter between 0 and 1. So your tree of depth L, and here, so you have your dynamics, but so let me explain what it is. F. So what is t hat x is, so you have your big tree here. So this is the big tree of depth L. You have some point x, okay? And so t hat is just the tree below x without x, okay? So without x, this is t hat x, okay? What I should say also about this constraint, since on the boundary you have all zeros here, and because of the choice of small l, if you are below some line, which is, so this is delta L, okay? If you are below this line, the constraint will be satisfied, okay? So all the side below, Cx is just 1, deterministically, okay? This is clear for everybody. Because of the 0 here, you know that the bootstrap map will just give you 2 0 as children. Okay, so this is one thing, and I need something different. So this is t at x, and so below x, I also use the following notation. I call delta x just the small tree that is below x at end of depth L, small l. Okay, so what's the lemma says? Somehow it says that you have some kind of spectral gap inequality, not for the usual dynamics, but with this one, with a constant which is just a constant. And this will help us at the end, because this will guarantee that below x you can find this line of 0. Then you will try to apply some comparison argument. So if I have time, I will say just a few words. So how do you prove this lemma? So I want to prove this lemma because here we use very much the fact that this is a tree, and we are at criticality using this fact. Okay, this is the main thing we.
Do
yes?
you know if it's true for entropy?
Sorry?
Do you know if the lemma is true for entropy?
No, actually we tried. Well, I don't know if it's not true, but what I know, if we don't know if it's true. Now we tried it. You'll see. We do some crude argument, like that you cannot do with the entropy because of x log x business. So proof of the lemma. So the starting point is an easy fact. So what is true is this. So it will be mu variance x. So this is just using repeatedly the conditional equality for the variance. This is easy. It's not there is nothing deep here. And then what you do, you just insert here the constraint you want to insert and the complement. So here you had this constraint plus the complement, and you use just the variance. So this is less than 2 times the sum of what you want. So this is what you want at the end, plus something that you would like to control. So what we would like to do is to control this guy, all this sum, by the constant less than 1 times this sum. Okay, this is our objective. So this is what we want at the end. And we just want to bring that on the other side of the inequality. And okay, so how do you do that? So let me take one of this guy. So already at this step, at this step you cannot do anything with the entropy. Well, maybe you need to be a bit more clever and do something else, I don't know. But our approach does not work. So I take one of this guy and I try to deal with. So the variance x of so I just use that this is less than the second moment. So mu, I can reconstruct tx here, or mu x, whatever. But since Cx, this constraint depends only on the this small tree delta x, I can bring it outside this mean. So here there is squared. So this, because this guy here depend only on what is inside delta x. Okay, so I can bring it outside this mean. Now I use Cauchy-Schwarz with respect to this measure. I bring the square inside, and at this point, the measure of this guy is just the constant 2 over L. So some constant over L times mu x of mu of tx squared. But if you take the proper normalization, you can from the beginning ask f to have mean 0 with respect to this measure. So this is nothing but the variance, sorry, mu, the variance dx of this guy. So you gain something because of this quantity. that is small. And so now I use this inequality here, but not on the whole tree, just on the small tree tx. Okay, I use it again, so I get constant over L, the sum over all y's that are in tx, but this quantity does not depend on what is outside delta x. So what you exactly need is what is in delta x and x of the variance. So there is a mu in tx of the variance y of mu of f. So I'm using just this inequality, but inside the small tree tx. So we are almost done. Now I just take the sum. So I'm back here. So let me call this guy I. So I will be less than 2 times what we need. So this is the good guy. Plus 2 times, so 2c over n, the sum over all x and the sum over all y's of mu of the variance mu tx. So there is a mu outside. Variance y of mu. So now I just have to invert the two sum. When I change the sum, what happens is now I want to sum over all y and to count how many x I have. So fix a y. So you fix a y somewhere and you ask how many x you have such that the delta x contains y. And actually you have at most delta L of them. So the ones that are above the y. I mean the father, grandfather. So at the end you get 2 times the good quantity. So inverting the sum, plus 2 times c over L times delta L. And here you get again the quantity on the left. So now L is 1 minus delta capital L. There is this delta here. So you take delta small enough, you bring this on the other part, and you get the lemma. Okay? So this ends the proof actually of the lemma. So you see, we used very much the fact that we had this quantity here. Maybe I want to say that. So here is an open question. So look at the system where you have, so it's 3 but you don't ask. Now the dynamic is not you ask all the children to be empty, but you ask just 2 of them, at least 2 of them to be empty. In order for this guy to make a flip, you ask that 2 of them, whatever the order, are empty. Okay? And you ask the same question. So here you can prove that the bootstrap map, all this business holds. The critical value is 8 over 9. And you ask what happens at critical points. Okay? But here the picture is very different. Because with probability 3 over 4, with positive probability, there is an infinite cluster. So there is an infinite cluster of 1. While here, the cluster of 1 with probability 2 over L, with high probability, you don't have a cluster longer than L. Okay, so the picture is very different here. Okay, so again, in the proof, we use very much this fact. So for this problem, we don't know how to do. So this is an open question. Okay, so this was the first step of the proof. How many time do I have? It's over. And now that's fine. No, actually,
No, I come from the Middle East. We can negotiate.
no. I'm fine. I wanted to show you that.
Okay.
I mean, the last part of the proof. Actually, I just wanted to do it by hand. So
Nothing. He's just warming up now.
You just arrived. No, so the second part, step 2, which I will not do precisely, is this kind of multi-scale analysis. So now this constraint somehow gives you guarantees that you have some line of 0 here somewhere. So what you want to do is to do what? To consider the system, instead of looking at the variance at site X, you just increase your set, and you look at the set that arrives till the border, the right border you have, guaranteed by this guy. So once you have the good border, you can apply the spectral gap that you know is something, okay? But you have this on scale L, so you can divide the scale L in various, heights. So let me maybe write the one intermediate step 2. So what you can prove after that is that the sum, which is on the right hand side here, no, sorry, variance X. Is less than some constant times. So there will be the sum of 1 to n or n minus 1, maybe. So what is Ti? Ti is just the inverse of the spectral gap of your operator, but for trees of lengths. So alpha is some parameter greater than 1. And so you have different scale. Okay, you will take like capital L to be alpha to the, say, n plus 1. Okay, you choose delta so that L, this small l is alpha to the n. Okay, and so at the end you can prove something of this type that you can at the end by induction just solve and prove the result. So again, the idea is you divide your size small l in various sizes of size alpha to the I. And once you have the line of 0 somewhere, say it's at distance alpha to the I, but not at distance alpha to the I plus 1 or something like that, then, or the converse, it's at this distance but not that one, then you enlarge the variance in order to get the good boundary condition. Then you apply the spectral gap at this level with some monotonicity. It will give you this Ti. Well, you have to play a little bit and you get the result. So it's probably better to stop here. Thank you.
Questions, comments?
I was wondering if the cluster attached to the root
Yes.
is itself Markovian, starting from if you start from U, you consider the subtree given by the cluster.
Yes.
I have the impression that it is Markovian. This one, because when you will attach, the problem is sometimes you will attach another cluster, but this one you don't know nothing about it, you know. So I was wondering, you consider for the lower bound as a upper bound of the spectral gap, the number of the points inside, but I think maybe something more subtle than that. For example, the isoperimetric constant associated to the comparison with the number of leave and total number of the.
But okay. But it should be true actually. L square should be the right answer. So yes.
Because maybe also there will be a comparison with this cluster, this evolution, with a evolving set. For instance, if you forbid to attach a cluster below, but just put one on, remove one on the boundary of the leaf. So maybe there could be a comparison.
But the cluster shouldn't be more. I mean, the cluster, if you have a big cluster and then it breaks.
But the cluster at the origin, because otherwise it won't be.
But don't you know? Don't you have some information 2 steps later that there's a good chance that it will connect again and you know it become large again? So suppose you have a big cluster that you know. So there's some memory, right, from like 2 steps ago that it can jump to what it was before or something.
Or maybe a comparison with evolving set.
Any more questions, comments? No?
Yeah, I have a question, sorry. Do you know if, in fact, you don't lose already something important at the first
Here? Yes, probably. We are losing, okay. I mentioned the paper by Aldous and Felix where they are doing this one-dimensional case. And so in 2008, the 4 of us, we reproved the same result, but also that includes many of the kinetic and constraint models, including the 2-dimensional ones, like Northeast, etc. Prove that there is a spectral gap. But the approach is, again, a kind of multi-scale analysis, but it doesn't work for the tree. And so we had to use this approach. Actually, this approach was in the paper by Martinelli, Sinclair, and Reitz. So they use something like that. So we don't have any. I mean, we don't have another option for that. Probably we are losing a lot, but I mean.
Because intuitively it would be tried for kind of affine functions and of the number of sides, but not for the kind of function that you use for the upper one.
Yes. You would like to have something more tight in order to get a better beta at the end?
No, but maybe if you lose everything here.
Yes. Yes. Right.
Okay, let's thank the speaker again. Problem session in 16 minutes. If you have a question, please hand me a piece of paper with your name and just the title of the problem.